All right, hello statisticians. I'm just going to do a quick walkthrough of the notes. We are starting Unit 4, which is our Chapter 6 and Chapter 7 in the textbook. So today we're going to talk about simulations to model probabilities. I'm going to try to get through this really quick so you have time to work on the assignment and enjoy the rest of your e-learning day. All right, so here we go. We're going to talk about probability. And probability is how likely is an event to occur. So what we're looking for is something that gives us that likelihood. So you've got subjective probability. That's when you kind of make it up, like I'm 99% sure I'm not going to have your test graded before Friday. Okay, so you would hear that 99% and say, well, not very likely, huh? There's also the classical approach to probability. That's when you have equally likely outcomes. And so you think, well, the chances of me flipping this coin and getting heads is 50% because there are two equally likely outcomes, heads and tails, and heads would be one of those two, which would be 50%. This is the same thing that tells you if you guess on a multiple choice question with 5 outcomes, if you're equally guessing, that's 1 out of 5, there's a 20% chance of getting that right. So classical probability works pretty well as long as you have equally likely outcomes, but sometimes it gets to the point where you can't really figure it out. It's too hard. So we have to come up with some other ways of doing this. Now, this is difficult to see with my little PowerPoint. I don't know where to put my face. Put me down here for a second. I don't know if that'll move. All right, so I'll put it back up there. So here's the idea with something called relative frequency. So this is when you're actually going out and counting things. So what we will see is that in a very, very long series of trials, the relative frequency of something happening gets pretty close to its true theoretical probability. For example, flipping a coin, we might not expect to get exactly 50% heads on any sequence of coin flips. But what you'll see is eventually that the truth, which is 50% chance of getting heads, that your probability of 50%, our relative frequency is getting really close to that. You know, so here you can see in the picture that the relative frequency is about 0.508 after 500 trials. And again, that's not 50% exactly, but it's pretty close. And what we start to see is kind of a limit. And our relative frequency starts to kind of hop around and then pretty much it sort of settles on a certain spot. And as soon as it settles on that spot, we know we've probably located that true probability, or it's a good estimate for that. So what we will use for this is this concept called the law of large numbers. Okay, so the law of large numbers says, and you see a little box of star right here, that the simulated probability, the empirical probabilities, when we actually go out and try something like flipping coins or rolling dice or drawing names out of hats or whatever we're doing, that those simulated probabilities get closer and closer to the true probability as the number of trials increases. Now, when we're talking about numbers of trials, though, for the law of large numbers, we're not talking about 10 or 20 or maybe even 100 or 200. We're talking about lots and lots and lots and lots and lots of trials. So eventually, we're probably not going to see a real accurate measurement of this until we get into those, tens of thousands of trials where we're going to start seeing this happen. Now, the law of large numbers, again, what we're going to see is eventually your relative frequency is going to get close to that true probability. What that does not mean is this, and sometimes we humans, we're really bad at math. We talked about how humans are bad at random. Well, we're also bad at probability sometimes because we have this idea that probability kind of owes us something, and it doesn't matter. We all do this, but what happens is, so let's say that I have this string you see in the middle. Okay, if I was going to flip a coin repeatedly, it means that the proportion of heads in my sample is going to get close to 50% for a very, very large sample. But what that doesn't mean is that I've gotten a whole bunch of heads in a row. I'm on like this hot streak here, and I've gotten all these heads in a row. It doesn't mean that the chance of tails is more likely or that the chance of heads is more likely, because probability doesn't owe me anything. The coin can't look back and go, oh no, I've been heads the last 9 times. I better be tails this time because eventually I got to work out to 50%. So on that 10th trial or that 12th trial, even if you've got a long string of heads, it is still a 50% chance of getting heads or a 50% chance of getting tails. Okay, so you got to get that out of your brain, that each time you do it, that it's not going to change that probability, that the probability can't look back and see the previous trials. Okay, so what you can do is you can use that kind of to your advantage. This idea of the law of large numbers. For example, let's say I'll give you $500 if you can flip a coin and get over 60% heads. And I'm going to give you a choice. Would you rather flip the coin 10 times, 100 times, or 10,000 times? All right, so here's the argument that you want in your head. I know that the more times that I flip the head, the closer my relative frequency is, the actual proportion of heads that I see in the flips, is going to get to 50%. So it's going to start off as going to be kind of all over the place. I may have a lot of heads or a lot of tails, and eventually it's going to kind of like level off. Okay, so the sooner the fewer amount of trials are more wild and all over the place, and the more trials, the closer it's going to get to 50%. But I'm not trying to get 50%, I'm trying to get 60%. So if I was going to bet on this, I would want to go the fewest number of trials, because the fewest number of trials, I am more likely to get something large, over 60%. Now, I might also get something really small, but if we're just talking about what's more likely here. The more times I flip this, the more it's going to be closer to 50%. It's going to start narrowing in, and my chances of getting over 60% are going to drop. Okay, so in order to do this, we've done this in class before. We've simulated events happening. A lot of times if we want to figure out what is the likelihood of something happening, like I've got my poster up here on the wall behind me, so I can tip this up here. Okay, so we had the is it sexual discrimination poster, and we talked about how likely is it to fire 5 or more women out of the sample of 10 if 30% of the company is women. So we can use simulation to set this up. And simulation is something where you assign numbers, or you assign a computer program, or you pull beans out of a little cup and you simulate what's actually happening. And you count the probability, and you do it over and over and over and over and over again. So it wasn't just one person in the room pulling beans out of the cup, it was everybody. And we put our numbers together and we calculate the probability of the relative frequency of what we see in our simulation. And so what's going to happen then is that we are allowed to, based on the law of large numbers, we're allowed to use those simulated or empirical probabilities to estimate what's actually going to be true, which is convenient for us because it allows us to calculate some probabilities before we maybe have the mathematical skill to do so, or sometimes it makes us able to see what's going on so that we don't even need to do those calculations. So for example, if I flip a coin 4 times, what's the probability that I'll get heads at least 2 times? Now, I could write out all the possibilities of coin flips here and could do that, but what's the fun in that? All right, so I'm going to simulate actually doing this here. All right, so to set up a simulation using a table of random digits, here's what you're going to do. The first thing you want to do is on a single trial, you want to say, what is the success rate? What is the probability of this thing I'm looking for? So I want to know what's the probability of getting heads. So that's 50%. The next thing you want to do is you want to take your digits. Now from 0 to 9, there are 10 digits, 1 through 9, and then the 0. That gives you 10 digits. And you want to assign 50% of those outcomes to be your winner there. So since heads has a 50% chance of happening, we'll say like 0, 1, 2, 3, and 4. 50% of the outcomes are going to say heads, and the other 50% are going to say tails. Okay? And then we are going to, it wants to know if I flip a coin 4 times, what's the chance I'm going to get heads at least twice? So what I'm going to do is I'm going to go to my random number table and I'm going to read 4 digits one by one. So my first trial here is 1, 5, 8, 3. Those are my 4 coin flips. Okay, and I'm going to record how many numbers are in the 0 to 4 range because those represent heads. So I see 1, 5, 8, 3. There's a 1 and a 3. Those are both 0 to 4. There's 2 of those. That gives me 2 heads in that set of coin flips. Okay, and then I'm going to do this again. I'm going to repeat this many times. So my next 4 digits would be 8, 4, 7, 1. You can see that down here, 8, 4, 7, 1. There are 2 numbers between 0 and 4. Those would be the 2 heads, okay, etc. So the next 4, I got 7, 4, 7, 6. There's only 1 head in that coin flip. 8, 6, 6, 1. There's only 1 heads in that coin flip. And 4, 3, 3, 0. Well, all 4 of those were heads, and that was a little streak there, right there. So there's 4 of those. Okay, so I just did 5 trials. Ultimately, you'd want to do this many times, like 100 times, but I'm not going to do that on that video. So Out of these 5 trials, I would want to know what's the probability of getting 2 or more heads in 4 coin flips. Well, according to this simulation, it's about 3 out of my 5 trials, 1, 2, 3, 4, 5 trials, and 3 of them were 2 or more. So it was about 60% chance in this little trial. Now, again, this is not enough times. You got to do this over and over and over again, and that gives you that idea. All right, so the other question, you hit a free throw shot about 75% of the time. Run a simulation to determine how many you will hit out of 20 shots. Okay, so again, the idea with this is that you're going to want to, a 75% chance of winning. So you think, okay, probably hit 75%. Now, if I use 0 to 9, that's 10 digits. And taking 75% of 10 digits is a little sketchy because 7.5. So instead, I'm going to use 00 to 99. 00 to 99 is 100 digits. Okay, so if I do 0 to 74, that's 1 to 74 is 74, plus the 00 gives me 75. Then 75 out of the 100 I can say are hits, and 75 to 99 are going to be a miss. Okay, and we want to know how many out of 20 shots would do this. So what I want to do is I want to look at every 2 digits on the table, 1, 5, 8, 3, 8, 4, 7, 1, etc. 1, 2, 3, 4, 5. Okay, every 2 digits, and I'm going to continue until I've looked at 20 pairs. And I'm going to see how many of them are from 00 up to 74. Those are going to be hits. And how many of them are not. Okay, and then we'll continue until we've looked at the 20 pairs. So I went through and I did this, and I looked 15, that was a hit, 83, miss, 84, miss, 71, miss, 74, hit. I think I said miss, but that was wrong. So 74 was a hit. So I did this all the way until I had looked at 20 pairs of numbers. And out of those 20 pairs of numbers, 15 were in that 0 to 74 range for being hits. Okay, now what you would eventually do is you would do this over and over and over again. You'd look at another set of 20 pairs and another set of 20 pairs, and you do that a whole bunch of times. And what that's going to do, you'd take your answer, and that would simulate about how many times would you expect to, out of 20 shots, to be hit. Now notice that that'd be 15 out of 20, which is really cool here because that is 75%. All right. So here's another one. It says, suppose there are 10 multiple choice questions on a quiz. Each question has 3 choices, A, B, and C for an answer. Unfortunately, you went to see a movie the night before and you were unprepared for the quiz, and you decide to guess the correct answers by just randomly choosing one of 3 choices. Okay, so we want to describe a simulation to estimate the probability of answering at least 4 of the 10 questions correct. Okay, so can you get at least 4 of the 10? Can you score 40% on this test? All right. Now, if you think about it, the probability of getting a correct guess is 1 out of 3 if there's 3 answer choices. And if I go 0 to 9, that's 10 digits. And it's really hard to do a third of 10 digits. It's like 3.3. That's weird. Okay, so I could do the 0 to 99 again. That would work. And then I could make 33 out of, so anyway, that's kind of weird. So instead, I think what I'm going to do is go 1 to 9. All right, so I'm going to assign 1 to 3. That would be 1, 2, and 3. 3 as correct guesses, and 4 to 9 as incorrect guesses, and I'm just going to flat out ignore the 0. Okay, so when I'm looking at there, 1 to 9 would be 9 digits. Okay, 3 of the 9 would give me that perfect 1/3, 30%. So it would simulate that probability appropriately. And I'm going to read the digits one by one, and I'm going to count how many I get in the interval 1 to 3. And since it's a 10-question quiz, each trial will consist of us looking at 10 digits, excluding the zeros. Okay, we do this over and over and over again and determine how many times you got at least 4 recorded. All right, so I look at my first set of 10 numbers here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's no zeros in that one. And so I would record how many are 1 to 3s, and I have 3 1 to 3s. So on this 10-question test simulation, we got a 3 out of 10 correct. So it didn't get quite my 4 out of 10. When I go to do this next one, 7 6 8 6 6 1 4 3 3 0. So I'm ignoring the 0. So I got to hop over and get one more digit on this one. And again, if I keep doing that, so I went ahead and did 5 trials here, and these are kind of messy, but I went went through each, I got 10 digits written down that were 1 to 9, excluding the zeros, and counted. And out of these 5 different simulations I run, there was only 1 out of the 5 where I got at least 4 questions correct. Notice that most of the time I got 3 on these simulations, which it'd be 3 out of 10 questions, which is 30%, which is pretty spot on for that 1/3. Okay, now I have one more question, and this one is just to kind of jog your brain of something that we talked about earlier in the semester. Okay, so this one says a population of TV viewers is normally distributed with a mean of 20 years, and my video may be covering this, so I'm sorry, and a standard deviation of 5 years. What percentage of the population has an age of 18 to 21? Okay, so if I want the area under a normal curve, remember in our calculator, we can do menu, statistics, distributions, and we can use that normal distribution command, norm CDF, to actually figure out the area under a normal curve and use that as a probability. So I gave myself a little sketch. Here's my normally distributed population. It has a mean of 20 and a standard deviation of 5 years. We want to know what percentage is between 18 to 22. So we want this little shaded region here. So I went to my calculator and I went to a scratch pad and I typed in menu, statistics, distributions, norm CDF, okay? And it gives you fields to fill in. So I've made the lower bound 18, the upper bound 21, the mean was 20, and the standard deviation was 5. And that ended up giving me, my calculator, the norm CDF, spit out 0.2346, so we can say about 23%. Okay, now we'll talk more about normal distribution again during second semester and refresh this. Just to remind you that sometimes the probability is not something you can just figure out. You have to go and calculate it first so that you can run your simulation. All right, so what we think is our population of TV viewers is about 23% 18 to 21-year-olds. All right, so if I wanted to simulate asking someone at random, what's your favorite show? What's your favorite show? So how many people do you interview before you get 4 people ages 18 to 21? And this time we're going to use a random number generator in our calculator to do this. So we use a random number generator. So I know 23% is the age we're looking for. And we want to know not how many out of 20 or out of 100, but like how many people do you have to talk to before you find 4 people who are 18 to 21 years old? All right, so I'm going to start off and I'm going to assign 1 to 23 to be my 18 to 21-year-olds, and then 24 to 100 to be my not 18 to 21 years old. So 1 to 100 is 100 numbers. 1 to 23 is 23. That's giving me my approximately 23% here. Since I'm not using a random number table, my random, I'm not going 00 to 99. If I use the random number table and did 1 to 100, I have to look at every 3 digits. All right, and then I'd have all those extras that I have to ignore. Okay, so this is easier here. So I'm going to use my random number generator in my calculator to start spitting out numbers from 1 to 100, and repeats are going to be okay. Because this represents the chips in a bag or something like this. So it's okay if we have some repeats in this case. We're not individually selecting people. We're not going to worry about that. So note if the value is 1 to 23. If it is, then you found somebody you were looking for. And you can continue until you found 4 values in that interval. You count the number of trials until that 4 success. And repeat that many times, find the average. Now, to do this, you always want to seed your calculator. I seeded my calculator with the number 1, 2, 3, 4. And then I did my random integer command like we did in the last chapter. And you're not going to have to do that for your homework, so don't stress out if you don't know the calculator commands for that. Remember, you can always use Siri to generate random numbers for you as well. All right, so the first time, my calculator spit out the number 3, and then 19, and then 10, and then 3. So I got 4 people between 18 to 21 right away, so 4 trial. The next time I had to work a little harder. It started off with a whole string of numbers that were not in the range, and then I got 3 in a row, and I got hopeful, and then I had a whole bunch more that were not in the range, and then finally, and it took me 19 to do that. So it took me 19. So I only had to interview 4 people the first time, but 19 the second time. And again, you would do this over and over and over and over again, and that should give you an idea of where this would be. All right, so big ideas, recap. What do you need to know? So you need to know that probability in general talks about if we were going to repeat this many, many, many times, we would expect this proportion of trials to have this result. So when I'm talking about the probability of heads being 50%, what I'm saying is if I flip a coin repeatedly a lot of times, many, many, many times, I would expect the proportion, the relative frequency of heads to approach 50%, to be approximately 50% after a significantly large amount of trials. The law of large numbers tells us that for that very, very long sequence of trials, our relative frequency approaches the true probability. So what happens is for short amount of trials, you're going to see it hopping up and down, and then eventually it's going to start leveling out. And when we start to see that limit of the relative frequencies, it's going to help us see where that true probability is, which is why simulations can help us model random behavior, because we can use the simulations to get lots and lots and lots and lots of trials. And from those lots and lots of trials, we can start seeing what the relative frequency is actually doing and use that as an estimate for the true probability, even if we don't calculate it by hand. And all the things that we've calculated today, all those probabilities, before the end of this unit, we will calculate mathematically without having to run a simulation. So remember, to set up a simulation, if you were going to describe the correct way to do this, you would need to figure out what percentage of the digits need to represent success, and then come right out and say that. I'm going to make 0, 1, 2, 3, 4. I'm going to make all the evens this, make all the odds that, something like that, so you know which digits represent success and which digits represent failure. And it's okay to ignore digits. Okay, if you're supposed to have a 50% chance, you could say, well, the 1 is success and the 2 is failure, and I'm going to ignore everything else. That's fine as long as you explain how. Then you'll explain your method. What are you counting? I'm going to count the numbers that are ones or evens or whatever. I'm going to stop once I've reached 20 trials. I'm going to stop when I find 4 successes. Explain how you're going to do that. Simulations always need to be repeated many, many times, which is why we put so many stickers up on those boards from previous. We want to see how many times those are. And at the end, you're usually going to take an average of all of those numbers. We're going to look and see what the trend is showing. Where does it look like the average is? Where's the mean? Or possibly the proportion. The proportion of 5 or more looked like it was about 17%. All right, so thank you much. I would recommend you watch the College Board videos over these topics. They're really good and they're really short, much shorter than my video. Okay, all right, have a good day. And pause.